Sometimes we just want to know if our series converges or diverges. We don't really care about what it converges to if it converges. We just want to know if it converges or diverges. And there are a bunch of tests, a lot of them, that we can use to test whether a series converges or diverges. The simplest among them is the divergence test. The divergence test is a test that tells us if a series diverges, but it's not good at telling us if a series converges. Then the next test after the divergence test is the integral test. So in this section, we're going to look at the divergence test and the integral test. We'll start with the divergence test. If the limit as k goes to infinity of ak is not equal to 0, then the series summation of ak diverges. All right. Now, let's do an example. All right, so the first example, so what we want to determine if series diverges. So how about the summation, the series summation k from 0 to infinity of k over k plus 1? Does this series diverge? Does it converge? Well, let's start with a divergence test. If the limit of ak is not equal to 0, then we conclude that it diverges. This is our ak, by the way. All right, so let's look at the limit of ak as k goes to infinity. This is the limit as k goes to infinity of k over k plus 1. Well, this is quite easy to see that the limit goes to 1, but let's look at it from another perspective. If we divide both the top and the bottom by k, we end up with 1 over 1 plus 1 over k. And this definitely goes to 0. So that means that this limit is 1. And it's not equal to 0. So for that reason, our limit, our series converges, diverges. Oh my gosh, series diverges. So let's talk a little bit more about this. If you have a bunch of numbers, so our AKs is A1. So we have AKs, think about it, A1, A2, A3, and we're adding all of them up. A4, and we just keep going. And this limit is not going to 0. It's not decreasing at all. All right? So think about a bunch of numbers that even though they might be decreasing, I unfortunately say they're not decreasing. They might be decreasing, but they're not going to 0. Right? So maybe they decrease or they increase, but the point is that they are not converging. This set of numbers is not converging to 0. And then you're adding all of them up. So at each point, you add a number to the series in the summation. You're adding a number that is not equal to 0, and it's not trying to be 0. So that means the series keeps increasing and increasing and doesn't converge. Let's try another example. Summation k from 0 to infinity, 1 plus 5 to the power of k over 3 to the power of k. All right, so our limit as k goes to infinity of ak, our ak in this case is 1 over 5 to the power of k over 3 to the power of k. So we're going limit from k to infinity of 1 plus 5 to the power of k, 3 to the power of k. So this is limit as k goes to infinity. We can divide each of the terms in the numerator by 3 to the power of k. So this is 1 over 3 to the power of k plus 5 over 3 to the power of k. All right. As k goes to infinity, the first term goes to 0. As k goes to infinity, the second term, this is greater than 1. This whole term is greater than 1. This is greater than 1. 5 over 3 is greater than 1. So k goes to infinity. So I have 0 plus infinity, which is not equal to 0. So series diverges. All right, so I'm going to introduce a term, a series. This series, summation k from 1 to infinity of 1 over k. This is a special series called the harmonic series. So this is like, this is 1. This is the harmonic sequence. Let's start with the sequence. 1, 1/2, 1/3, 1/4, 1/5. So this is a sequence. So the series, this series is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. Okay. So let's look at this. This is the limit as, if we check the test, limit as k goes to infinity of ak is the limit as k goes to infinity of 1 over k. And this is 0. So what does our test say? Our test says that if it's not equal to 0, then we conclude that it diverges. But if it's equal to 0, we can't say anything. It doesn't mean it converges. So this test is inconclusive. But later on, we're going to be able to show that the harmonic series actually, diverges. It diverges, but remember that it diverges, but this test doesn't work. This test is not strong enough to show us that it diverges. Now, I want you to show, try this. Apply the test to this one. Apply the divergence test to this. So this is 2e to the power of negative k. Right. So tell me your check it. What's your answer? Does it convert? Does it diverge? Is the test inconclusive? If it's inconclusive, then what other test can you apply to it? What other test that we have learned can you apply to this? What kind of series is this? All right. So think of what kind of series it is. We've learned a series, a class of series that this particular series belongs to. Let's do another test. The integral test. All right. Now let's suppose the function f is a continuous, is continuous, or well, is a continuous positive decreasing function for t greater than or equal to 0. And then let's let ak be equal to f of k. For k equals 1, 2, 3, and so forth. Then there is certain things we can conclude. Then the series k from 1 to infinity of ak and the series 1 to infinity of f of x dx both converges, or either both converges or diverges. Okay. And we have to note that the values are not necessarily equal. So this is a big theorem that needs an example for us to be able to explain it. So let's start with an example. So we want to determine convergence. Does it converge? Does it diverge? We have summation k from 3 to infinity of k over k squared plus 1. Does this series diverge? Does it converge? Okay. All right. So the integral test says, suppose f is a continuous positive decreasing function for t greater than or equal to 0, and let ak be equal to f of k. So let's start with f. So our f, what we can do is let's choose f of x. Let your f of x be equal to x over x squared plus 1. What do we know? F is continuous. All right. What else do we know? F is increasing. Why? F is increasing because if you use, think of Calc 1, if you find the derivative and the derivative is always less than, F is decreasing, F is decreasing, we want it to be decreasing. So F is decreasing because if you look at the derivative is 1 minus x squared over x squared plus 1 squared. I want you to check it. So this derivative is always less than 0 for x greater than 1. I want you to check it. So let's look at the integral test again. It says f has to be continuous. We've checked that our f is continuous. F has to be positive. Our function is always positive. It's always positive, so maybe we should also mark that down. Right? So here, f is positive for x are greater than or equal to 3, right? So this, we can actually say greater than or equal to 3 here, since our series starts, our case starts from 3. All right, what else do we need to know? F is decreasing. I kind of argue that it's decreasing, and I want you to check that it's decreasing. So we've satisfied all the 3 conditions that we need in order to make our conclusion. So now, to make our conclusion, we need to find the integral. The integral of x over x squared plus 1 dx, the integral from 1 to infinity. We could also do the integral from 3 to infinity. It doesn't matter. So maybe let's do it from 3 to infinity. Maybe 1 is actually easier to deal with, to infinity. So I'm just saying 3 because our series starts from 3. K starts from 3. But if the series starts from 1 and it converges, then from 3 would definitely converge. And if it starts from 1 and it diverges, if it starts from 3, it diverges still. So it doesn't really matter. But you know what? I'm going to change this question, make it more in line with the theorem. So let's just change everything to 1. Change this to 1. And make this also 1, okay? So forget about the 3. Okay, so that we can do this integral, x over x squared plus 1 dx. This integral is the integral. If you use substitution and everything, you're going to end up with this expression, x squared plus 1, and then you're going from 1 to b. This limit is going to give you infinity. So if you have any problem with this, please look at section, I forgot what section that is. I think it's section 8-9, yeah. Improper integrals. So this integral is definitely infinity. So what does our theorem say? The theorem says that if the integral, that our series is going to behave like our integral. So our series and our integral both converges or diverges. So since the integral here diverges, therefore our series k from 1 to infinity of k over k squared plus 1 must diverge. All right. Now, let's try another one. So let's try k from 0 to infinity of one over k squared plus 4. Now, again, f of x, choose your f of x to be, we can say let f of x be 1 over x squared plus 4. So we need to check that f is continuous. F is definitely decreasing. Check that. F is decreasing. What else? F is positive. Yeah, what am I thinking? F is always positive. no matter what number you plug in, any number from 1, from k equals 1, give you positive. So, all right. So let's say for all this thing for k greater than or equal to 1. Or maybe in this case, let's do for k greater than or equal to 0, since our integral for x greater than or equal to 0. Pardon me, because our integral starts from 0. Okay. Now, let us now try our integral from 0 to infinity of f of x dx is the integral from 0 to infinity of 1 over x squared plus 4. So we can see it as the limit as b goes to infinity of the integral from 0 to b of 1 over x squared plus 4 dx. So it's the integral, the limit b goes to infinity of, actually is 1/2 the inverse tangent of x over 2. And then you're plugging in 0 and b. And if you plug this in, you get limit as b goes to infinity of, or we can factor out the 1/2, why not? Limit as b goes to infinity of inverse tangent of b over 2 minus the inverse tangent of 0. All right? The inverse tangent of 0 is definitely 0. Inverse tangent of b over 2 as b goes to infinity is pi. So this is just going to be 1/2 times pi, just pi over 2. So we can conclude that, therefore, series converges because this converges. The integral converges. Okay. Now, I want you to try one. Now, we looked at the harmonic series. How about the harmonic series? And I told you that the harmonic series diverges. I want you to use the integral test to show that the harmonic series actually diverges. Okay? So your f of x in this case is 1 over x, is decreasing, is continuous, and then you find the integral from 1 to infinity of 1 over x, and you just show that it diverges. So apply the integral tests here and show that it diverges. I'm just going to write integral test shows that this series diverges. Okay. All right. So there is another series that I'm going to introduce. It's called the P series. It's like a generalization of the harmonic series. So P series is k from 1 to infinity of 1 over x. Oh, no. 1 over k to the power of p. So the harmonic series is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so forth. So the P series is 1 over 1 to the power of p plus 1 over 2 to the power of p plus 1 over 3 to the power of p and so forth. Okay. The convergence or divergence of this series will depend on the value of P. So for instance, if P is 1, then we just end up with a harmonic series. We just end up with a harmonic series which diverges. Okay? Think about that. End up with a harmonic series which diverges. But if P is greater than 1, say P is 2, then we don't know. We don't know what we're going to end up with. All right? We don't know if it diverges or converges. I kind of know, but I want you to find out. So what I want you to do is apply the integral test to this series. Do it case by case. Do case 1 where P is equal to 1, and then do case 2. Case 2, case 1 where P is equal to 1, and then do case 2 where P is not equal to 1. Okay, and then you're going to have two subcases. You're going to have a result for when P is greater than 1 and when P is less than 1. We've done stuff like this. So it turns out that when P is greater than 1, the series converges. And when C is less than 1, the series diverges. Okay. So with this, we can end up with a theorem that says, a little theorem, that says that the P series, this series, K from 1 to infinity of 1 over K to the power of P, converges. It converges for P greater than 1 and diverges. And diverges. For P less than or equal to 1. Okay? And then this is now a result we can keep using. So I want you to think of, so far, all we've done about series. There are 3 special series that we've met so far. The first one is the geometric series. The second one is the harmonic series. And the third one is the P series. Those are the special types of series we've met so far. And it turns out that the P series is actually a generalization of the harmonic series. The harmonic series is a type of P series, but it's very, what do I say? It's special. It has its properties that makes it unique. All right, we're going to stop here. We're going to continue in class. I would like you to try all these exercises I asked you to try so we can talk about them in class. All right, see you.